Hi everyone, we're starting section 16C on exponential functions and graphs of exponential functions. So essentially what we're going to be doing in this section is we're going to be looking at how to graph exponential functions and what the exponential function looks like as we graph it. Just like we did the quadratic function and we saw that a quadratic looks like a parabola, we're going to take a look at what the exponential function looks like. All right. So when we're talking about exponential functions, what we're doing is we're looking at quantities that increase or decrease by a fixed percentage. And we describe that by saying that it's an exponential function. So we're going to be looking at exponentials. We're going to be solving exponential equations using algebraic methods, which we've already done. As you recall, we did it in sections 16A, B, G, and H. And we're going to also look at using logarithms. All right, so we know that an exponential function has the variable part, or the variable occurs in the exponent. Okay, so for example, y equals 2 to the power of x, or y equals 3 to the power of x, or y equals 4 to the power of x, for example. What do each of these mean? It means 2 to the power of x means that every next value is going to be twice, in this case, every next value is going to be double the previous value. So that if I started with 1 and 2, so if my value of x was 1 and my value of y was 2, if my value of x was 1, that means that when I place in the equation y equals 2 to the power of x, my value of y goes to 2. Now if I place 2 for x, that goes to 4. If I place 3, as you can see, it's 3 times as much, so it's 2 times 2 times 2, which goes to 8, and then 4 would go to 16, and so forth, and 5 would go to 32, and so forth. Notice that what's happening here is that this isn't doubling, this is doubling every time, so the next value is always going to be double the previous value. So this increased by 4, this was increasing by 2, by 4, by 6, by 8, and then by 16. All right, so we're looking at a doubling, okay, in this case, of the previous values. If we were looking at y equals 3 to the power of x, well, that would mean that every next value is 3 times the previous value. So if I started with x equaling 1, my y is equal to 3. If I place x equaling 2, y goes to 9. If I place x equals 3, y goes to 27. So I am multiplying. So what I'm doing is I'm multiplying by 3. I'm multiplying by 3. The next one would be times 3, which would be 81 in this case, and so forth. And again, the same thing is over here on the right-hand side with the squaring. It's times 2, times 2, times 2, times 2. And the same thing would occur with y equaling 4 to the power of x. So if I was given as a starting question, and you were asked for the function f of x equals 3 minus 2 to the power of negative x, okay, I'm just going to make this a little bigger, then, and you're asked to place in f to the power of 0, what that means is that I've got 3 minus 2 to the power of 0, so I place 0 in for x, and since 2 to the power of 0 is equal to 1, then I have 3 minus 1, which gives me 2. Now if I were to place in here f at 3, that would become 3 minus 2 to the power of negative 3, and 2 to the negative 3 is like saying 1 over 2 cubed, which is 1 over 8, so it's 3 minus 1/8, which becomes then 2 and 7/8, which is the same thing as saying 23 over 8, or 2 and 7/8. And if we were looking at the next example, the very last example here, it would be f to the negative x. So what are we doing? We are replacing negative x for x. So wherever there's an x, I replace it with negative x. So since it is found to be 3 minus 2 to the negative x, it becomes 2 to the negative x, and that becomes 3 minus 2 to the x. All right, So let's just start looking at the graph. Now, I kind of gave you already a hint, or I gave a brief explanation at the beginning of this lesson of what the exponential graph looks like. But here's our actual graph. So what we're going to do is we write down our XY table. So here are my values of the X and my values of the Y that come in. So this is my input, and I'm going to have the output. So I'm going to put in my values of X inside this equation, which is f of X equals a to the power of X, or rather 2 to the power of X. And from there, I will get my corresponding Y values. So all that means is I will do f at -3, that equals 2 to the power of X, which will be equal to 2 to the power of -3, and that equals 1/8, or 1 over 2 cubed. Remember that it equals 1 over 2 cubed from our laws of the indices, which becomes 1/8. Now, so I placed in a value of X that was -3 to get a corresponding value of Y, which was 1/8. So when I graph that, I do -3, and 1/8 is approximately here. Okay, it's an approximation. If I then do f at -2, it gives me, again, from 2 to the power of X, it will be 2 to the power of -2, which becomes 1 over 2 squared, and that makes it equal to 1/4. So I go to -2 and 1/4, which is right here. My next one is f at -1, which equals 2 to the power of -1, and that goes to 1 over 2 to the power of 1, which equals 1/2. Therefore, at -1, my value of X at -1 is going to have a Y of 1/2. And there it is. Now, what's happening is that our graph is increasing. It's called exponential growth in this case. Okay? So the graph is increasing. So what does exponential growth actually mean? It means that you start off with small numbers. When we start off with small numbers, there's a gradual increase. And you can see that the increase is gradual here, from -3 to -2 to -1, all the way to 0. It's a gradual increase. So when I put in 2 to the power of 0, I get 2 to the power of 0 here. That goes to 1. So I know that at 0, my value is 1. And now, as I start getting to larger numbers, such as 1, 2, 3, and possibly 4, 5, 6, etc., what happens is that exponential growth starts to go up at a much faster rate. That's why we call it exponential. That's what we also hear very often on the news when there is something that's growing at an exponential rate. For example, one of the more common things that we hear if you're doing biology or chemistry and so forth, is you certainly hear in biology that a bacteria grows at a rate of, it doubles every 10 minutes, or it doubles every half hour, or something. So that is an incredible amount of bacteria that are being reproduced if they are doubling every half hour. Now, it doesn't seem like much, but let's go to 5, 6, 7, go to 24 hours, and then we'll see how many bacteria there are. Okay, if we were to get to 24 hours, for example, that would be a lot of bacteria, because it would mean 2 to the power of 24. Okay, and that's a large number. That's a very, very large number. All right, so this is what our graph looks like. Now, the one thing that you should get out of this, now taking a look at the graph, I'm just going to get rid of this. Now, taking a look at the graph, what you should see, like I said, is that the graph increases slowly when the numbers are very small, but then it starts to shoot up quite quickly as the numbers start getting larger. And as the numbers get larger and larger, the graph becomes more steep and at a faster rate, obviously. So the graph is doubling at a much faster rate. All right, so another thing that we should notice, though, about this is that we have a y-intercept. And our y-intercept is found at 1. So that's kind of an interesting thing that you may want to hold on to and to think about. Keep that in the back of your mind. And that the graph is going to be completely above the y-axis. Now, why would it be completely above the y-axis? Because if we saw, even if I had done 2 to the power of negative 4. So we had negative 4 that gave us negative 3 that gave us 1/8. If I had done negative 4 or 2 to the negative 5, this would have become 1 over 16. This would have become 1 over 32. 2 to the power of 6 or negative 6 would have become 1 over 64. And all of these numbers are always larger than 0. So there is no number that is ever going to make that go to less than 0 or even equal to 0. So what we end up having here is that our graph not only is above the y-axis, but we also create, or we have, a horizontal asymptote. Remember that the horizontal asymptote is that line where the values of y get closer and closer to 0, but they never actually reach 0. So we say that the line y equals 0 is going to be the horizontal asymptote of the function. Now, does it always have to be 0? No, it doesn't, because we'll see when we look at the transformations, it could move up and down, okay, to other places on the graph. All right, so let's take a look at our first graph. So if we have y equals a to the power of x, okay? This is called our base. We already know that this is our base, the a, and the value of x is going to be our exponent or our power. All right, now, the base, I'm calling it a, but it could be called b, it could be called a lot of different other variables, but it's usually a or b, okay? And for all the exponential functions that we have, okay, so f of x equals a of x. There's my exponential function, where the value of a is going to be either 2, 3, 4, 5, 6. It could be also, it could also be numbers between 0 and 1, all right? But for those, for those, it's going to be increasing. So if I have the value, okay, of a, so if my value of a is bigger than 1, okay, as you would have seen in the investigation, if my value of a is larger than 1, then the graph is going to be an increasing graph. And if my value of a is between 0 and 1, that would be, the graph would be decreasing. So if a is bigger than 1, we're going to have exponential growth. And if the value of a is between 0 and 1, we're going to have exponential decay, or it's decreasing. All right, so when we take a look at it, we can see, if we look at this, let's look at the blue line on the first one. We've got y equaling 2 to the power of x, and then we have y equaling 3 to the power of x. So what does that mean? That if I had y equaling 4 to the power of x, I'm quite certain that y equals 4 to the power of x would be something like this in red. It's the red graph that I've just placed in here. So y equals 4 to the power of x. So what does that basically tell us? It tells us that as the graph, as the numbers of the value of a get larger, or they move away from 1, the graph is becoming steeper. Okay? So that means the graph is going to become steeper. Now, if our graph is between 0 and 1, if we take a look at this, well, look at the green graph again. We have 0.5, so 0.5, which is 1/2, and then we have 0.3, which is 0.3, which is 3 over 10. So 5 over 10 here, or 0.5, 3 over 10 there. It would appear that as the numbers are getting smaller, okay, the graph is getting closer to the y-axis. So I'm pretty certain, again, right here, that if I were to pick y equals, let's say, 0.1, for example, to the power of x, I'm quite certain that my graph would be closer to the y-axis. Okay? So the graph of f of x equaling a of x becomes steeper as a moves further away from 1. So as the values of a get larger, greater than 1, the graph is increasing, and therefore it's increasing. And what that means is that it's getting closer to the y-axis as the values of y get larger. And as we're looking at a decreasing graph and the values of a are between 0 and 1, then that means my graph, as my values are getting smaller, they are getting closer to the, they're getting closer to the y-axis. All right, so let's take a look at, perhaps we can sorry about that. There was about a minute where I paused, and I thought I had paused, but I hadn't. So sorry, you probably, I hope you kind of went ahead on that. There was a lot of silence there for a second. All right, so if we wanted to take an example, we could take an example and do a quick graph of y equaling 2 to the power of x. Well, we've kind of already done 2 to the power of x. Let's do 2 to the x. And then we do y equals 1/2 to the power of x. Now 1/2 to the power of x is really like saying, keep in mind, it's really like saying 2 to the power of -1, which is to the x, which is just 2 to the negative x. So 1/2 x and 2 to the negative x are exactly the same thing. So if I were to graph y equals 2 to the power of x, now as we saw earlier, so we could start at -3, so the -1, -2, -3, -4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, so that I can do 2 to the power of -3 would be 1/8, 2 to the power of -2 would be 1/4, 2 to the power of -1 would be 1/2, and then 2 to the power of 0 would be 1, and then 2 to the power of 1 would be 2, 2 to the power of 2 would be 4, as you can see that it's going up faster, and 2 to the power of 3 would go up to 8. Therefore, 2 to the power of 4 will be up here somewhere at 16. Okay, and when we graph it, it will look as such. And notice that our y-intercept is found at 0, 1, and our graph is always going to get closer and closer to the x-axis, but it's not going to cross it. Okay. Now, if we wanted to graph very quickly the next one, so the next one would be 1/2 to the power of x, or 2 to the power of -x, same thing, all right? Then we would have, here's our graph. So we would have 1, 2, 3, 4, -1, well, we don't need -2, -3, -4, -1, -2, -3, -4, 1, 2, 3, 4. All right, so in this case, we would have, if I started with 2 to the -3, that would be -1/8. So when I have x being -3, sorry, it would be +1/8. So -3 would be, made an error there. Okay, so if we have 2 to the power of -x, we're going to do this properly. We'll do it proper. So that if I had x equaling -3, then this would go to 2 to the power of -3, which would go to 2 to the third, which equals 8. So it would be 3, -3, and 1, 2, 3, 4, 5, 6, 7, 8. Now if I had -2, it would become 2 to the power of -2, which would go to 2 squared, and that would go to 4. So at -2, it would go to 1, 2, 3, 4. Now I'm pretty certain that 2 to the -1 if I had 2 to the negative 1, that would go to 2 to the minus 1, which would go to 2, and therefore I would have negative 1 and 2. Then I would end up again with, if I had 2 to the power of 0, it would still give me 1, okay? So that I would have this at 0. And then again, if I had to have 2 to the power of negative 1, that would go to negative 1 to 1/2. Then it would go to 1/4, and then 1/8, and then 1/16, and so forth. And as you can see, the graph is going through exponential decay. Whereas the other graph, this is decay, whereas the other graph is going to be exponential growth. And again, don't forget to place your x and y's, your origin, 1, 1, your zeros, your origin, and your scale. Okay, now let's take a look at what happens when we are doing a translation. So we're looking at translations now, and it's not unlike the quadratics, except now instead of looking at x squared, so we know when we looked at x squared plus k, that was the parabola, the standard parabola, and then you moved it up k units or k units down. Well, that's exactly what we have now, except we have the regular, we've got the regular exponential graph, which is a to the power of x plus k. So that means that when I have a to the power of x plus k, what we're going to look at is y equals, it's the movement of the a to the x graph along the y-axis. So this is moving along the y-axis. So it's vertical. So we know that this is a vertical movement. And so we are shown here that it is going through a translation of 0k. It's only the y values that get affected, k number of units. So if the value of k is bigger than 0, then the graph moves up k number of units. If k is less than 0, the graph moves down k number of units. Now, if we have the graph of the form y equals a to the power of x minus k, remember that what's being affected here is the x value. So if it's the x value that is affected, okay, then that means that it's the horizontal translation of the graph. Now, it says here that you move your graph k units if k is bigger than 0, and it moves to the right, and if k is less than 0, the graph moves to the left. Now keep in mind that if I had x minus 3, this means it's moving to the right. Okay, remember that it's the same thing as we did with the quadratics. So it's moving right, and if I had x plus 3, that means it's moving 3 units to the left. Okay, so because what we're saying is if k is less than 0, then we have, for example, a to the x minus negative 3. So it's negative 3, k is less than 0, but look what happens. It goes to x plus 3, which means that it's actually moving left. Okay, and the one that says minus is actually moving right. All right. So that if we were to take a look at the graph here, let's sketch the graph of y equals 2 to the power of x plus 3. Now, what we do is we take the y equals 2 to the power of x, so that's our base graph. We take our 2 to the power of x graph, and we move all the y values up 3 units. Okay, now in doing that, okay, what you need to realize, and that's not a hard part, that's the easy part. Okay, you just take you take your regular y equals a to the power of x, or your 2 to the power of x graph in this case, all right, and you just shift it up 3 units. But what you need to see is that when you're shifting it up 3 units, what's also shifting up is the horizontal asymptote. And in moving the horizontal asymptote, that means that the horizontal asymptote is no longer found at 0, but it's going to be found at y equaling 3, because it's been moved up 3 units. If I were now looking at the second graph, y equals 3 to the power of x minus 4, well, what that would require would be for me to first graph the y equals 3 to the x graph. So first I would graph 3 to the x. So the 3 to the x graph is going to look exactly the same as the 2 to the x, except it's going to be a little bit steeper. So the 2 to the x would be over here. The 3 to the x would be here, approximately. And from there, I would just take my 3 to the x graph, and because it's x minus 4, it's affecting only the x values, then I would move my graph horizontally 4 units to the right. Okay? So that, that would cover that. Now, if we want to take a look at now the stretches, so we're looking at the stretches of the graph. Okay? So again, if we were to have y equals k times a to the x, so that means that what's being affected by the k is the y values. So we are doing a vertical dilation of k units with a scale factor of k. So if k is going to be greater than 1, then that means that the graph is going to get steeper and it's moving away from the x-axis. Okay, so it's getting steeper and it's getting thinner. If the value of k is going to be between 0 and 1, then the graph is going to move towards the x-axis. So that would be an example of a vertical stretch. Now, if we were looking at a horizontal stretch, remember that it affects the x values if we're looking at a horizontal stretch. So what the graph looks like is a to the power of x over k. So we are taking the y equals a to the power of x graph, and we're going to dilate by x with a scale factor of k. So if k is going to be greater than 1, then the graph moves away from the y-axis. And if the value of k is between 0 and 1, then the graph is going to move towards the y-axis. All right, so let's take a look at an example. Okay, so our example would be the first one, A. So if we look at the second graph in part B, y equals x over 3, that means that that should be y equals x over k, by the way. They made an error here. This should be y equals 2 to the power of x over k, where our value of k, in this case, is equal to 3. Okay, so their scale factor was 3 here. All right, so that's where the 3 is coming from. All right, so what does this mean? It means that as our values in the denominator of this fraction, as the values get larger, this number overall, though, of the fraction is going to get smaller, which means that my values of the y, rather than increasing, the values of the y are going to decrease. I hope that makes sense to everyone. Keep in mind that it's x over k, 2 to the power of x over k. If my values of the k get larger, so if I had x over 2, or x over 3, or x over 4, or 5, okay, that would mean that overall, this number is getting smaller every time. So the number here is small, this one will be smaller, x over 3 will be smaller, and x over 5 will even be smaller. But when I'm looking at 2 raised to the power of the smallest of these numbers, which is x over 5, it means that the values of the y are going to be smaller, and therefore they are going to be going away from the graph is going to be moving away from the y-axis. All right. Then the very last one is very, very simple. This is, again, what we did with quadratics. So if we have a minus or a negative in front, remember when we had negative x squared? So again, with the quadratics, when we had y equaling negative x squared, that meant that we had a reflection over the x-axis. And when we had y equaling negative x squared, for example, okay, that might not be the best example here, but if we had a negative x, that means it's a reflection over the y-axis. So the same thing occurs even with the exponential functions. So if I had to sketch, if I have the graph of the form y equals negative a to the x, we reflect y equals a over x in the x-axis, y equals a to the power of x in the x-axis. And if we have y equaling a to the negative x, so what's getting affected here is the x values. They're obtained by reflecting y equals a to the x in the y-axis. Okay, so we're going to sketch the graph of y equals negative 4 to the power of x. So you would start by graphing the 4 to the power of x graph, and then the negative of that means that you're just going to take all the y values and turn them into the opposite sign, and therefore the graph will be facing downwards. Okay? So if it's facing downwards, we have the reflection over the x-axis. Now, if we take a look at y equaling 3 to the negative x, that means I'm going to graph y equals 3 to the power of x first. And then from there, once I have graphed the y equals 3, so as I was saying, we take the y equals 3 to the power of x graph, we graph that first, and then 3 to the negative x means that it's going to be reflected over the y-axis, which means that the only values that are going to change are going to be the x values. Okay. That pretty much covers it. Now your work to complete would be the textbook exercise 16. See all of it, and then you'll have a handout found on Google Drive called exercise 18B.1 and 18B.2, and you'll be responsible for all of that. All right, see you next time.